Hello and welcome to Introduction to Business Analytics. My name is Hari Raj Gopalan and I'll be your instructor for this lecture. So we are deep into predictive analytics and we have been talking for a long time about regression, multiple regression. We finished categorical variables and today we're going to talk about interactions. Now remember, interaction is the effect of one variable on the dependent variable depends upon another variable. And we did this when we did ANOVA. Remember ANOVA, we did a taste test and we looked at the impact of a food condiment on enjoyment. But the food condiment's effect on enjoyment depended on the food. So mustard on hot dogs increased overall enjoyment. Hot chocolate on ice cream increased overall enjoyment, but mustard on ice cream or hot chocolate on a hot dog had a completely different effect. So while food condiment did affect enjoyment, it affected it based on what food it is. So interaction effect is often called the it depends effect. Let's take an example here of how interaction effects look. Here you have sales of Toyota, Hyundai, Honda, and Suzuki. And here are the different continents: Europe, blue; Asia, red; Americas in green. And here you don't see any interaction. Consistently, Toyota is being outperformed by Hyundai, Honda, and Suzuki at the best. And it doesn't matter which continent they are. There is no interaction. These lines are all parallel. But if you take a look here, now you'll see that in Europe, Toyota performs the worst. Toyota's performance in Europe is less than Asia, less than Americas. So Americas is the best performance, but for Hyundai now, you would see that their performance in Asia is the worst, whereas America and Europe is pretty much the same. In Honda performs better in Europe than in the Americas, and Suzuki too. So here there is some interaction effect. And if we flip this where we have Europe, Asia, and America as the x-axis, and each of these lines as Toyota, Hyundai, and Suzuki, would also see a different effect there. But this is the example of having no interaction versus having an interaction. So let's look at an example where we have this manufacturing process. We are looking at the product strength, and the product strength depends on temperature, pressure, and time. And we're going to look at an example of how this affects each one affects strength. So let's take a look, and let's take a look at the scatter plots of these variables. So if you look at the data, here is the relationship between temperature and strength. Now, it looks like there's this big blob here for temperature. It doesn't really give us any linear relationship there. With respect to time, it does look like there is more the time there's a sharp decline in strength. With respect to pressure, again, so pressure, it looks like there is some increase to strength, but again, there's this big circular blob. So the question is, we try to figure out what is going on. Time might have a negative linear relationship, but pressure and temperature doesn't seem to affect strength much. But we know that temperature and pressure must affect strength because we have this, it's basic physics or science. And so when we look at direct effects, we're saying temperature affects strength, pressure affects strength, time affects strength. Let's run it like a normal regression just to see what's happening. Here we are saying temperature, pressure, and time affect strength. We're running the multiple regression. and we get an adjusted R square of 85.9%, and standard error is 3.18. Whatever the units the strength is 3.18. Model is very significant, but as we run it here, we can see temperature has a p-value of 9.25%, which is not significant. So we run it again using backward elimination, and we continue the process with just the two, and we get the final model. So pressure and time. Time is a negative variable. Pressure is a very small coefficient here, and they both affect the strength. Adjusted R squared is 84.78. So adjusted R squared is 84.78. Now remember, when we use temperature, our adjusted R squared was higher. It was 85 point something percent. So by removing temperature, while we have all the p-values positive, we actually are adjusted R squared, our explanatory value is actually reduced. So what's going on? So it is possible that temperature and pressure are linked together in some way. We know that material strength is affected by temperature because this is from basic science. We know scientific theory. And here it's coming out non-significant. So what's going on? So if you have done physics or you just listen to the Vedger channel, you know that temperature and pressure often affect each other. High temperature creates low pressure, low temperature creates high pressure. So is there an interaction between temperature and pressure? So let's take a look. We do have this final model here, but maybe we need to explore a little bit more. So let's look at the interaction. So for interaction, the first thing we need to do is to look at average values. So let's discretize temperature and pressure. And what we're doing here is we're sorting the data based on pressure from lowest to the highest. And I will go into Excel and show you this. I'm not going to show you the Excel part for doing the full model because we've already done it, but this one I'm going to show you. And we're going to find the average for temperature and pressure for each of those values. And then if a particular cell is less than the average, we say it's low, otherwise it's high. And then we find the average strength for low pressure and low temperature, low pressure and high temperature, and then we plot it on a graph line. If the lines are parallel, there is no interaction. If the lines cross, there is an interaction. So let's go to Excel and take a look at this. So as I said earlier, the first step is to get the average temperature and average pressure, and then you can create a function here which says if this temperature value is less than the average, if B2, which is this value, is less than the average, then it's L, otherwise low temperature, otherwise it's high temperature. And if you put the right dollar signs properly, now you do the same thing for pressure. If C2 is less than, it's L, otherwise it's H, and then you can copy these down. Once you do that, you can find the average. And essentially we are sorting everything here according to pressure because we want to make sure we can get the average high temperature for low pressure, average strength when things have high temperature for low pressure, and so on. So here we go. We are selecting average, and the range is your temperature here, which has low pressure, right? And then you're going to say if this is L, find the average of the strength. Similarly here, in this particular case, you're finding the same area, you're finding the average if the value criteria is H. And similarly, you do for your other two, and you get the averages. When you have low pressure and low temperature, the average is 95.46 is the strength. Low pressure, high temperature, it's 93. and here it's the high pressure. And you can then do your plot this, and you basically have a line diagram which shows you for pressure and strength for different temperatures. So you can see low when you have when you're looking at high pressure, right, and you're looking at temperature for low, it's 91, and then when it's high temperature, it's 90. It doesn't change that much when you have high pressure under high pressure environment. However, under low pressure environment, it drops quite dramatically. Your temperature, strength of the product drops quite a lot more when it's under low pressure and you have high heat. So obviously, pressure affects how temperature affects strength, right? So pressure affects how temperature affects strength. And that is your interaction effect. So if we go to the interaction effect, this is what we did. We sorted the data first, and then we created this by essentially finding the average strength of low pressure, low temperature, low pressure, high temperature, etc., using the average if function. And here we go. We looked at low temperature under high pressure. There is no change from low to high. The strength pretty much remains constant. In fact, it increases slightly. But under low pressure, when you go from low temperature to high temperature, the strength actually declines. So there is no parallel. There could be an interaction here. Let's see if this interaction is significant. So we're going to create a new variable called interaction, and then we're going to multiply each value of temperature and pressure to get these values and run backward elimination. So you see here, we've taken each value of temperature and pressure and multiplied it to get a new variable here. And we run backward elimination again to get these results. And you can see all of them are significant. So which gives us our final model, which essentially gives us the right where temperature, pressure, and temperature times pressure are all significant. Let's go to Excel and talk a little bit more about what we did. So very quickly, because we have done this so many times, what we have done is we have created a new variable called T multiplied by P, or interaction. And you can see that there is your interaction effect. You basically multiply those two values, and then you go to data analysis, and you do the same thing. Your Y range is this, your X range is essentially all of these variables, and you run the whole thing, which gives you your final model. As you can see here, the residual plots for temperature are on both sides. Residual plots for pressure, time, so they are on both sides. And then you can see the normal probability plot. It's not kind of straight line. You can definitely see a curve here. But then given that you're multiplying two variables, this is not a linear model anymore. You're actually going into nonlinear models. So interactions, we have the final model here with the interaction. And so we have temperature, pressure, and time affecting strength. And then also pressure affects how temperature affects strengths. So you should be able to, with this final model, build confidence intervals, predict strength of the material using other values of temperature, pressure, and time. This is very similar to what you did before. And these interaction effects also make the model nonlinear because you're multiplying now two variables. And we'll talk more about nonlinear models in the next lecture.